Hello, everyone. Thanks for coming to my talk. Today, I'm going to talk about zkDL, an efficient zero-knowledge proof of deep learning. My name is Hongyang Zhang. I'm currently an assistant professor at University of Waterloo and the Vector Institute for AI. So AI regulation is almost everywhere, and this work is about AI regulation on copyright protection. We have seen many news on journal which reported the importance of AI regulation. For example, in as early as 2023, ChatGPT was reported to be banned in Italy over data privacy concerns. And the CNN business also reported that Getty Images suing the makers of popular AI art tool for stealing photos. And in Europe, MEP is ready to negotiate first ever rules for safe and transparent AI. And also another example is the EU AI Act as early as 2023. There's one item called Obligations for General Purpose AI, which highlighted that detailed summaries of the copyright data used for their training will also have to be made publicly available. So that is a requirement from the government about the AI to the AI companies. However, although AI regulation is pretty important, it can make sure that protects the privacy, protects the copyrights of users. However, AI regulation is also double-sided. For example, in 2023, OpenAI CEO Sam Altman mentioned that they may consider leave the EU if AI regulations bite. So what we could deliver in this work is a proof system which enable OpenAI to prove to the government about two things. One is about the proof of training logic. The training actually follows certain logic. And also the second thing that OpenAI could prove to the government is that they can provide a proof of data membership, whether a given data belong to the training data set of OpenAI's GPT. At the same time, we can also help protect OpenAI's privacy, OpenAI's business secrets by keeping the training data and their model checkpoints are secrets. And our solution to achieve this goal is a so-called zero-knowledge proof system, also known as ZKP. And in ZKP language, there's a prover, there's also a verifier, and the prover can correspond to OpenAI. The verifier can correspond to the government. OpenAI want to prove to the government that their model training actually follows certain given circuit C. And they also have their secrets W. For example, the W can correspond to their training data sets or say their checkpoints. And with also certain public input X, OpenAI want to prove to the government that the output that they get, for example, as a 10, is indeed calculated from the given circuit C by plugging in their secret W and the public data 1 into this function C. And that corresponds to in the AI language, the prover corresponds to the OpenAI, the AI companies. The verifier corresponds to the government who want to do the AI regulation. And the given circuit C can correspond to the forward pass and the backward pass for the large language model training. So OpenAI want to prove to the government that the model that they get actually indeed follow the forward pass and the backward pass as they claim. And the secret and witness W correspond to the private model parameters, private model weights, and the training data sets that they use. And the public input X correspond to the public data or those kind of hyperparameters that they use during the training. And eventually, the expression Y is equal to C of W and X correspond to OpenAI correctly training the model by the claimed algorithm such as gradient descent. So one application of our proof system is that before, Stanford scientists find that yes, ChatGPT is getting more and more stupid. However, OpenAI's VP products at that moment, Peter mentioned that no, we haven't made the GPT dumber. Quite the opposite. We make each new version smarter than the previous version. And our proof system actually allow OpenAI to prove to the public that they are indeed using the latest version to do the inference rather than the older version. So this is an application and the GPT ID. For example, when the user inputs a prompt where is University of Waterloo into a black box that's OpenAI is serving, and the model output it is as Waterloo, Canada, our proof system allow OpenAI to see the model behind the black box is actually GPT-4 rather than the previous version such as GPT 3.5. And before we introducing our methodology, let's firstly look at the limitation of existing ZKP system, such as zkSNORC. And there are many pros and cons for the existing ZKP system. As for the pros, the existing ZKP system can efficiently prove arithmetic circuitry. They are pretty good at arithmetic circuits, such as plus, minus, multiplication, division. And examples of arithmetic circuit includes matrix multiplication in MLP. When we do the linear transformation layer, we are doing the matrix vector multiplication, and this is a kind of arithmetic operation because all the operation consists of only plus, minus, multiplication, or division. And another example is that when we do the convolutional neural network, we have the convolutional operation, and we can do that by fast Fourier transformation FFT. And the second benefit of doing existing ZKP is that the proof size is pretty small. It typically only consists of log size of that of the circuit size. And thirdly, existing ZKP, the verifying time is pretty quick, pretty small. So that is a benefit. However, as of the cons, although existing ZKP systems, they are pretty good at arithmetic circuits calculation, but they cannot prove non-arithmetic operation. A non-arithmetic operation typically consists of a nonlinear activation function, such as ReLU, softmax, and so on and so forth. And also, we know that for the neural network, typically it is consists of one linear layer followed by another nonlinear activation function followed by another linear layer. So that being said, typically one arithmetic operation will follow the non-arithmetic operation followed by another arithmetic operation. However, it's still unclear how to connect the proof for the non-arithmetic operation with the proof of arithmetic operations. So it's harder to connect the two kinds of operations. And thirdly, for the cons, it's about the proof generation time. So that's the major bottleneck for the existing ZKP system. So here is a proof generation time of inference of one data on MLP. And here the x-axis refer to the size of a neural network from 2 million to 20 million. And the y-axis refer to the time in seconds. And we can see that for the vanilla inference time, it's only required 0.003 seconds on GPU. However, if we do that on the existing ZKP system to provide the proof generation time can be as large as 62 seconds. So even the fastest, the previous state-of-the-art ZKP system can be hundreds or thousands of times slower than the vanilla inference time. So our work tried to solve this issue. But before introducing our work, let's look at deep learning 101. Because we care about the deep learning training, so we know the deep learning training consists of two parts, the forward pass and the backward pass. For the forward pass, we begin with an input. We call it X. And firstly, we do a linear transformation layer So we multiply X with the weight matrix in the first layer, and we get the output for the first layer. It's called Z1. And it is a arithmetic operation. So we use a green to denote this arithmetic operation, and we use solid line to denote this arithmetic operation. And next, we need to do a non-arithmetic operation, the so-called ReLU. So for the ReLU, we can write the Z as two parts. One is we take the sign, and then we take the absolute value, and then we do the element-wise multiplication. We get the output of A. So this is a non-arithmetic operation, so we use a red to denote the operation is non-arithmetic, and we use a dash line to denote this is a non-arithmetic operation. Once we have A, then it follows by another linear transformation layer. We multiply A with the weight matrix in the second layer W2, and we get the output Z2. And with Z2, we can calculate the loss. Let's say we use MSE loss. We compare Z2 with the true label that we are interested in, and then we can get the loss function. So that is how we do the forward pass. For the backward pass, we do the reverse process. We begin from the loss. We firstly calculate the gradients with respect to Z2. So we use GZ2 to denote this is the gradient with respect to Z2. And this is equal to Z2 minus Y because we are using MSE loss. And the next operation, because we do the backward pass, the next operation is this operation. So this is a linear operation, a arithmetic operation. So we can also do this using the chain rule. So we get the gradient with respect to Z2, we multiply with A1, and we get the gradient with respect to W2. That is, we get the gradient with respect to the weight of the second layer. So we want to continue doing the chain rule, and we go into another non-arithmetic operation, that is the ReLU. And for the ReLU, we can also decompose everything as a sign, and also the gradient in the next layer, and we do the element-wise multiplication, and we get the gradient with respect to Z1. So that helps us to get the gradient with respect to into the first layer, and then we just use the chain rule again to go into this layer, and this layer we calculate the gradients by another arithmetic operation. So you can see throughout the whole process, it typically like arithmetic operation followed by another non-arithmetic operation followed by another arithmetic operation for the forward pass, and for the backward pass it's the same. And all the problem come from the ReLU given by the dash line here. And in order to solve this non-arithmetic proof problem, we propose the zkDL. And the idea here is that for the arithmetic operation given by the solid line, we use the existing proof system such as zk-SNRK. But for the dash line, the non-arithmetic operation, we use a bit decomposition. And we provide the proof of the bit decomposition to show that the bit decomposition actually works, and that finishes the proof. And for the proof of bit decomposition, in order to prove that the Z is indeed can be decomposed as the element-wise multiplication between the sign and the absolute value. So we firstly get a sign, and we use 1 to denote the value is positive, and we use 0 to denote the value is negative. And for the absolute value, we get 3250. However, we already mentioned that for the sign multiplied with the absolute value, we get a Z. This is a non-arithmetic operation, so it's harder to call the existing zk-SNRK or zkP system. And in order to do that, we further do the bit decomposition for the absolute value. For example, we know 3 can be represented by 011, 2 can be represented by 010, and 5 can be represented by 101, and 0 can be represented by 000. So once we do the bit decomposition, next we want to prove two things. Firstly, we want to prove that the bit decomposition is indeed in binary, so that all the elements are in the set 0 or 1. And in order to do that, we only need to prove the whole the arithmetic operation expression holds true by showing x times 1 minus x equal to 0. And this is a arithmetic operation, so we can use the existing system to prove that it's true. And secondly, we want to prove that the bit decomposition can recover the original by firstly recover the sign. So we use 1011 times 2 minus 1, then we can recover positive or negative. And then we do the element-wise multiplication with the absolute value. We try to recover the absolute value by expanding the binary representation into the original expression. So we multiply 2 to the power 0 with the last column, 2 to the power 1 with the middle column, and 2 to the power 2 with the first column. Then we can recover the absolute value, and then we do the element-wise multiplication with the sign, we can recover the z. And once we prove this expression holds true, this actually proves that the bit decomposition recovers the original. And also we notice that everything here, just the plus, minus, multiplication or division. So everything here can be is a arithmetic. Everything here is an arithmetic operation. So this can be also done by calling existing the zkP system. So in that way, by doing the bit decomposition, we can reduce the problem. Although original the problem is non-arithmetic, we can reduce it to an arithmetic operation proof. And another thing we want to solve is that for the modern neural network, it may consist of thousands of layers, so it can be quite deep. If we do the proof one layer by another, that can be quite inefficient, especially for super deep neural network. So in order to do that, we do the random linear combination to combine all the layers together into one layer, and then we provide the proof for this layer. So that being said, actually we are doing the proof in parallel across different layers. And no matter how deep the neural network is, actually we are doing one layer proof. So that's complete the work that we want to introduce today, the zkDL. So zkDL is actually there's another proof system for deep neural network training. It can actually reduce a non-arithmetic operation to arithmetic zkP protocol, so that we can call existing zkP system for the arithmetic operation to prove things, to prove the neural network actually works. And the way we do that is by bit decomposition. We can reduce the non-arithmetic operation to arithmetic operation. And also, the zkDL system also compressed the whole neural network proof system using parallelization and random linear combination. It's actually reduced the proof size by the depth of neural network. It's also reduced the proof time by the depth of neural network. Therefore, proving a 1,000 layer neural network is equal to proving a 1 layer neural network, because we use a random linear combination to combine all 1,000 layers together into just one layer, and we just prove for this one layer. So that can speed up everything by more than 1,000x. Comparing with if we do the proof one layer after another in a sequential way. So lastly, I want to mention some of the experiments that we have done for the zkDL system. So the first experiment is proving generation time and the size for a 2-layer neural network. Everything was run on CPU. And we vary the width of the neural network, so 2-layer neural network, from 64 to 256 to 1K to even 4K. And the number of parameters of the neural network ranges from 8K to 130K to 2 million or even to 33 million. So we can see, and also we vary the batch size from 16 to 32 to 64 and also 128. So 128 can be a very realistic setup in practice. So typically people train the neural network with batch size 128. And we compare our zkDL system compared with the previous SOTA in ZKP. And we can see, for example, when the neural network is as large as 33 million number of parameters, our system for large batch size 128 only requires 25 seconds to generate the proof. And the proof size is also controllable as small as 70 KB. However, for the previous best node SOTA, it's required more than 1K or even 10K seconds to finish the proof generation. And also the size is also large as 24 KB, which is larger than our 70 KB. And this is for 33 million. The same conclusion can also be made across different other hyperparameter, other architecture as well, such as 2 million, 130K million, and 130K, and also 8K. In terms of the size and time, we are much better than the previous SOTA for 2-layer. And also, we mentioned that the major benefits of zkDL is for the deep neural network because we do the compression. And this experiment shows the proof generation time and the size for multi-layer neural network. So here the x-axis refers to the number of layers from 2 to 4 to 8 to 16. And the first row shows the proof generation time. The second row shows the proof size. And we can see the dashed line correspond to our method, and the solid line correspond to our previous SOTA method by Liu et al. And we can see for the proving time, when the number of layers increase, the previous SOTA will increase the proving time. However, if we look at the dashed line, we keep a constant. So that being said, no matter how deep our neural network is always the proof generation time, the cost is always the same. And this happens when the neural network width is 64 to 56, 1K, or even 4K. And for the proof size, the improvement is more significant. We can see the previous SOTA results with the number of layers increase is actually exponentially increase the proof size. However, our method is roughly a constant as well, just because we do the random linear combination, we do the compression, and we compress everything into just one layer proof, so that the proof size and proving generation time is always a constant. So that's a benefit from our compression techniques. And we also, to contribute to the community, we also open source everything, open source our software, especially on GPU. And that is the zkDL. There's not a proof of deep learning on CUDA. We all open source everything on GitHub using this QR code. If you are interested, you can scan this QR code to get access to our open source code. So zkDL is a specialized backend that provides there's not a proof for deep learning powered by CUDA with 1,000 or even 10,000 speed up in standard zkML benchmark. So this is the first zkML implementation with CUDA support. Everything can be run on GPU, and it's pretty fast. It's 1K to 10K speed up on the standard zkML benchmark. Everything is open source. The whole pipeline is open source, and it's very easy to be used. It's very easy to be extensible. So it's compatible with PyTorch and support customized backbone, so you can use the software for your own backbone, for your own architecture, and for your own applications. So you can find the QR code here. And here is the results of our software running on GPU on the modular benchmark. So as we mentioned, we can see although the previous best node results requires 62 seconds to provide a proof, our method only requires 0.03 seconds. So this is roughly in the same level as a vanilla inference. And this also achieved more than 2000x speed up compared with the previous best node results. So in conclusion, in this work, we introduced zkDL. For example, on 10 million number parameter neural network with batch size 64, we can provide a proof in 1 second per batch. However, for the existing ZKP system, it's require roughly 1 hour for the general purpose ZKP. And as of the next step, for this work, we mainly handle the ReLU so that we can provide the proof for the ReLU neural network. The next step, we are going to support more non-arithmetic structure, such as softmax, such as other activation function, and so on and so forth. So that will be our next step. And you can find our software here in this QR code. And we also have the paper published here in IEEE TIFFs. And this is my email address. If you have any question, feel free to contact me by email. And I'm more than happy to answer any of your questions. Thank you so much for your attention.